Hello. I don't see anyone has joined, so let's wait. Hello? Hello. Yeah, I think I'm audible clearly, but let's wait for others to join. Hi, Saransh.
Hi, Bhumik.
Hi, Rohi. I think we can give it a start. Let others join in as well. Let me share my screen and let's go through some of the distributions. So, until last to last day, we looked into probability density function. We looked into cumulative density function. And now we are going to look into the rest of the probability distribution. Hi, all. I'm sorry, I think I got disconnected. So let me just share my screen once more. I hope you can hear me, right? Hello?
Hello.
Hi, Rohi, you can hear me, right?
Yes, yes.
Okay, okay. Let's give it a start. Hopefully you can see my screen as well. So until the last session, we have looked into probability functions. We looked into probability density function, which helps us give a very rough idea of what may happen. So I would like to quickly recap this. We had a clear case of a data which was represented in form of x and y axis. And then we had things like the histogram. So we had blocks like these, which represented the histogram or the distribution of the data, which looked something similar to this. So what we called a probability density function is that I will simply say that I'm going to take a smooth or a smoothened curve. So example, I'm going to take a curve which is something like this. This curve may approximately represent the data, the distribution of the data. So on y-axis, I have the frequency, and on x-axis, I have the class intervals. Okay. So basis the class intervals and the frequency, I create a function which is something like this. Now, when I create a function which is something like this, and later on we'll look into code as well, please don't get confused when you not see frequency on y-axis, because when we plot this, especially in Python, or that may well be the case with some other statistical tools. I have no such experience with other tools. I've mainly worked into Python and R. But what I have seen is this axis, so the values in the y-axis is going to change to something which is the probability or the cumulative frequency. Okay, so I can either call this the probability or the cumulative frequency because it tries to take an approximation, because that is how these visualization tools are going to display a probability density function or a cumulative density function. But please don't get confused. It is exactly the same thing as we have seen over here. And then we started looking into cumulative density function, which is something like this. So let me just draw it over here. So it goes something like this. Over a period of time, it has this kind of, let's say, data, and then the data gets summed up, and after a certain point in time, it's going to decrease. This one that I have drawn over here is the cumulative density function, because it is taking a cumulative. It is taking a sum of the events which are happening in each and every stage. So this one or this height is summed up with this height or this height and this height and so on, and then it is put somewhere over here. So this thing that you are seeing over here, when represented onto the y-axis, you will find all the visualization tools are going to represent this as the percentage or as the probability. So you will find a decimal number usually over here. We also looked into the fact that what is the advantage of using a CDF over PDF, because if, let's say, I try to draw a line which is something like this, and it intersects at a value of xi, okay, so it intersects at a value of xi over here, I can clearly say that in this CDF and in this, if this value of yi, which is over here, is, let's say, equal to 0.82, okay, and this value over here xi is equal to, I don't know, 1.3. So out of all of the data of x that belongs onto the x-axis, and I have xi which is equal to 1.3, 82% of the values fall within the range of this, which is the starting point, up to 1.3. Please note that this may or may not be 0. Okay, just because x and y axis is actually intersecting over here doesn't mean that the value starts from 0. This value or this range is going to be defined by the minimum and the maximum values of the variable x, or the variable which is plotted on the x-axis, right? So it may not start at 0. Maybe it starts at 0.9. So from 0.9, I have data until, I don't know, 1.8. Okay, so from 0.9 being the starting point, I have data until 1.8. So that's the range. This is the minimum and this is the maximum. So I can say that 82% of my data falls between 0.9 and 1.3 inclusive. Right, so this is the objective of doing a CDF over a PDF, because PDF shows me the overall graph. I can tell you that this range of data is going to give me the maximum value, or the maximum values are within this range of, let's say, I don't know, 0.95 to 1.1, right? So that's all PDF does, but CDF goes a level further. Okay, the CDF will be very much in use when we start taking more examples, and especially when we start taking examples of cases where we have more than one variable to compare with each other with respect to their distributions. That's where it's going to come into place. But let's not look into that right now. Let's look into this. So probability distribution is what we have already defined in the last session. I'll just quickly do a recap. What I am essentially trying to do over a period of time, I'm trying to plot what is the observed distribution of any event or any random variable. And then the data that I collect to plot this distribution will be basis its occurrence or the probability of occurrence. So this is exactly what I'm going to do when I'm doing a probability distribution. It is not a density anymore. I'm not trying to look into how dense or how not dense the things are. Okay, now I'm trying to look into something else. Right. So we will start, or we should ideally start with the normal distribution, but that we won't do. We won't do that because there is a reason. The reason will be clear when we look into normal distribution at a later stage. But we will start into things or into distribution which may or may not be normal. Now, what I mean by normal is that a distribution is said to be normal, or also called a Gaussian distribution or a standard normal distribution, in case the distribution changes equally and has a non-changeable average. So I may have a distribution which has a very good mean, and I'm not going to tell you what that mean is. If you want, you can read, but as of now, it won't make sense if I tell you what is going to be the mean, because there is only one mean which any normal distribution can have. Any normal distribution, any data which is normally distributed is going to have a single mean, and that value of that mean is known. I don't have to calculate that. If it is a normal distribution, there is always a single value of mean. There is a single value of variation or variance or the standard deviation. And that value is equal. So on the left hand side as well as on the right hand side, it's going to increase and decrease in the same way. But we will look into this later. Why? Because our objective is to understand these or more like these and understand in what cases they are used and why we need to convert ideal condition, a Poisson or a binomial distribution, into a normal distribution so that you can apply some statistical techniques on top of it. So that's what we are going to do. So let's start with binomial distribution. Binomial distribution, why we are starting with this is because this is one of the most widely used when it comes to industry. Industry means it may or may not be applicable in our IT industry, but in many or especially in the manufacturing or quality control kind of cases, it is very, very well used because is one of the distributions which helps us understand if X is going to happen or Y is going to happen. So as the name suggests, it is a binomial distribution, right? So if I want to write what is the definition, let me just copy this and put it over here. The binomial distribution deals with output of two categories only. Okay, so the output of the variable that we're trying to look at, the outcome of the experiment can either be head or tail. It can be true or false. It can be yes or no, and so on. So let's say I want to classify an email if it is a spam email or not. The I don't know is not going to be an acceptable answer in this case. Either I classify that email as a spam or I don't. I say that the mail is spam. So that is answer one, or type of answer one. Type of answer two, the mail is not a spam. As simple as that. So only two categories is where a binomial distribution applies. Why is this so important? Is because this is widely used in quality control, because as you can clearly relate, in quality control we may want to know if there is a defective product or no, and if there is a defective product, then we may want to find out what is the root cause. But first of all, I need to know what is the probability of a machine producing, let's say, defective outcomes or defective products in the line of the machinery that I have in my factory floor, or whether or not, let's say, in IT, a very common term is a software bug. So if I'm getting a bug, if I'm getting a defect, is that really a launch defect or not? So let's say if getting that defect is going to stop me from launching my software in the market or no. So should I mandatorily solve that problem in my code before I launch, or it is okay to live with that error right now? Let's launch the minimal viable product, and then at a later stage, maybe we are going to fix that problem by creating some kind of a task or a ticket in the backlog, right? So binomial distribution uh, is not only used in the industry over a period of time, it is also used in service organizations like banks, and then it is used in, let's say, insurance as well. But before we start applying binomial distribution, or we understand what all are the properties, I'll not call them the properties, I'll say properties slash conditions. There are a few conditions which applies to binomial distribution. The first condition, or let me just start in a different way. The conditions which is applied are all basis a process which is known as Bernoulli's process. You may have heard that name, or the principles or formulas that this person has created during his lifetime. and that we have already used in many mathematical as well as in physical areas. Mainly in physics, we have used a lot of the Bernoulli's theorems and the processes. Also in maths, the contribution is not negligible at all. So basis the Bernoulli process or the Bernoulli's theorems, we are going to look into certain characteristics which a binomial distribution is going to have. Now, why do we need to know the characteristics? Is because to do reverse engineering. Why I say this is because if I know the characteristic and if I see that characteristic in a distribution in a data which Rohi has or in a data which Sarangs has, then basis the characteristics I can say, okay, this data, because it has so and so characteristics. Hi all. I think again because of a network issue I got thrown out. Let me just reshare my screen. Hope you are able to see my screen and you are able to hear me. Basis which let's continue. So what I was saying is basis if I know the properties of, let's say, a binomial distribution basis the Bernoulli's process, I can look at these characteristics in the distribution of a certain variable and I can comment that this distribution is going to be a binomial distribution. So the first and the most important one is that all trials or experiments are independent and random. Okay, we have already seen what are independent events. So that's exactly what I'm trying to say here. All events or trials or experiments are entirely independent with each other and random. I have no pattern and they are entirely independent. So example given, if I'm getting a wrong product in the manufacturing chain, it has nothing to do with getting a right product because these two events occurring are independent of each other. Then I have, no, I shouldn't write we have fixed number of trials in the experiment. Seems there is some repetitive kind of a problem. I'm getting thrown out from Zoom a lot of times. Okay, so yeah, so the second is we have a fixed number of trials in the experiment. The third is, as I have already told you, there can only be two possible outcomes of the experiment. I think somebody is trying to say something. Is that so? Are there any questions from any one of you?
No, Bhumik.
Okay, okay. So yes, the third point is there can only be
Not
two. Sorry. I think there was a network issue there as well. So let me continue. So the fourth and most important thing is the probability of success. Okay, so in these experiments, we are going to get a success and a failure. We have two outcomes. We classify one as success and the other one as failure. Which one we consider success and which one we consider a failure is dependent on the question. Now, if there is a success and if there is a failure, the probability of success or getting a success is uniform throughout the number of trials. So if I have performed 10 trials or 10 experiments, all the events that are found in those experiments are independent and random. Their occurrence is entirely random. This number 10 is fixed. You are not supposed to change it. Please don't say, I don't like that number, let's make it 11. No. If it is a 10, it is a 10. Then there can be only two possible outcomes. In each and every experiment, I can have only two events, head or tail, yes or no, spam or not spam, good customer or bad customer. Should I give loan or should I not give loan? Right? Should I increase the credit limit in the credit card or no? That's all. Okay. And then the probability of success is uniform throughout the number of trials. So there is nobody ideally who is affecting the probability of success. Now, since we have looked into the characteristics, let's now go into the properties. Okay, so in theory, any binomial distribution has two inputs, I will say. So if you are going to write, or when you understand binomial probability, let's say you are writing a code into Python. Yeah, I think I'm back again. Let me share my screen. Okay, so what I was saying is, any binomial distribution, let's say you're trying to write that as form of a Python code. So let's say you have defined a function bin. So this function will take two inputs. One is n and one is p. Okay, that is the usual standard. Okay, this is also, or a binomial distribution in some books, you will also find it is called a discrete probability distribution. Why is that the case? Because you have either one or two, right? So you either have a value which is one, or you either have a value which is two. That's it. Asking a yes no question. Now, what is this p and what is this n, right? So the desired outcome, let's say you have a success, you have a failure, you are interested in looking into success, then the probability is defined by p, and n is the number of trials that you are going to get, or you are going to perform, which is going to be fixed. For the entire life cycle of the experiment, the value of n will be fixed. You will fix the value of n and then do only that many number of experiments and come up with a result, right? Now, if and only if you are doing only one experiment, then it is also known as a Bernoulli distribution. Why is that so? Is because, okay, let me write this first. So here P refers to the probability of the desired outcome. Okay, and N refers to number of experiments. Okay, N is the number of experiments, P refers to the probability of the desired outcome. If N is equal to 1, binomial distribution is also called Bernoulli's distribution or a Bernoulli trial. Okay, because the theorems proposed by Bernoulli is only done once in their lifetime. Okay, now let's continue from there. So what we are doing here is, let's say we are doing an experiment and then we find that, let's say, the probability of having any such case of getting a yes and no. So let's take an example. Okay, so we are going to take an example. Let's say we are doing kind of a head and tail kind of thing, or an experiment where each has an equally likely probability to happen. So let's say we are doing a coin toss and we are doing a head and tail. So what we are going to do here is we are going to plot the distribution. Let me just close this, and we say something like this. So I have a y-axis and I have an x-axis. I'm also going to tell you what this x and y-axis is going to mean. Okay, but first of all, we need to look into what is uh, the distribution itself. Okay, so first of all, in this kind of a distribution, what happens is this y-axis, or the one which is on the y, is going to give you the probability. So let's say I have created this bin as 0.1, and then 0.2, 0.3, 0.4, and 0.5, 6, 7, 8, 9, 10, right? So probability can range from 0 to 1. So in this case, this intersection is 0. In this case, I'm not saying for all the case, in this case. And then on X, okay, I have the number of trials. Okay, I'm back once more. There seems to be some very weird kind of a problem going on. Okay, I think we do have some time left. Let's try to see how much we can finish here. So I have y-axis, I have x-axis. So on x, I have the number of trials. On y, I have the probability. So as I said, I've already divided probability, which can range between 0 and 1. And I have already divided this y-axis into 10 single units, right? I hope there are 10 lines. Now what I am doing an experimentation. Okay, so for each and every iteration, let's say I have selected p, and p, let's say, is equal to 0.5. P is going to be the outcome actually, and then n. So number of the iterations. So let's say I have done 5. I've done 5 experiments. I got a probability of 0.2. Then I did 10 experiments. If I do 10 experiments, I get a probability of, let's say, 0.4. Then I do 20 experiments, I get a probability of 0.5. Okay, which is somewhere here. So let's say 0.5 is something like this. Okay, and then I do, let's say, 25 experiments. I get a less probability of getting the success or the yes answer, or the answer that I'm actually looking for. Let's say I do a 30, and again I get something related to 1.2. So if I now try to draw a smooth line between these points, this is known as the Bernoulli distribution, because I'm trying to find out something which is yes or no. And then there are other properties that we have already looked into. There are fixed number. So now this is going to be confusing. You might say, why are we changing the number of iterations here? We are changing the number of iterations per experiment, or not for each experiment, sorry. So if this one is 5, this experiment is done only once. Then after end of that experiment, I'm doing another one. Then at the end of that experiment, I'm doing another one, and so on. So the n is constant for the lifetime of that specific experiment. So it does not apply to another experiment. In another experiment, in another life cycle, the value of n can change. You can try to increase that. That is what we usually do. So to prove what we want to prove, we increase the number of experiments which we are going to do. And then we are going to arrive at a point when we are going to look into the graph and see how it is going. Now, this is a very typical graph. Why this is a very typical graph is because you may not always find a graph which is so well in shape. So if you look at this shape also represents something known as a bell curve, right? So it is a very, very good kind of a shape, and it is like a really nice kind of a shape, because if you draw a line between the middle point, which is like 20 over here, on the left hand side and the right hand side, you will find the synchronicity. So there is kind of a synchronous behavior or shape on both the sides of the middle line, right? So this is the meaning of that graph. So now that I have drawn this graph, what if I would like to draw the cumulative distribution function? So for each and every probability distribution that we are looking over here, I can also have a cumulative distribution function. Okay, and that cumulative distribution function is almost the same as the cumulative density function. Okay, but what we are going to do over here is, on the y-axis, now we are going to have the probabilities. So we have all the probabilities 0 to 1 into 10 equally spaced sentences. Now here we have, let's say, starts from 0. Then I have the number of trials 5, number of trials 10, number of trials 20, number of trials equal to 30, number of trials equal to 40. If I start taking a cumulative graph, you will see that for this line that I have drawn on the left hand side, the cumulative graph looks something like this. So this is the cumulative distribution function, which applies, okay, to the binomial distribution, which we have seen over here, which is a very nice shape. And if you try to add the values, it will look something like this. Please remember this shape, because when we are going to do the machine learning, this shape is really going to come handy for one very important machine learning algorithm. I'll just tell you the name. If out of interest you want to look into Google, you can do that. It's known as logistic regression. It's an algorithm which we use, or a method which we use to answer questions like yes, no. And this is the way the distribution falls in that case. So knowing the CDF of a Bernoulli distribution is so important, okay, or it is important because of this reason, right? So this is the Bernoulli distribution in all, but not all of the Bernoulli distribution is going to be so beautiful. Okay, there will be Bernoulli distributions which will look left skewed or right skewed, so something like this. Okay, or you may have a Bernoulli distribution which is going to look something like this. If you have a Bernoulli distribution which looks something like this, approximately its CDF, okay, can be drawn as well, and it is going to look a bit more clumsier than this. You see there is a good shape over here going on, a nice smoothness was there, but in this case there is an upfront rise and then there is a steepness, right? If it is a case like this red one, right, which is kind of a right skewed thing, this green one is a left skewed thing. So in case of a right skewed kind of a distribution, the the density function or the cumulative density function will even be more squeezed, right? But for a very good kind of a binomial kind of a distribution, let's say, it is going to be a very smooth kind of a thing. So this pink one is the best choice, or I can say this is really the best choice to have. This green one is something which you see as the left skewed one, or the red one which you see is something as the right skewed one. So this is what a Bernoulli distribution is all about. A Bernoulli distribution comes into picture when you are trying to do n number of experiments, one in each trial, as we have seen. So number of trials are fixed per experiment. Okay, if I do 5 experiments or 20 experiments, the number of trials can change. And then basis the change in number of trials, I observe the probability of the occurrence of my favorable outcome, the outcome that I'm trying to look for. And then I plot a graph like this. It may look like this. It may also look like this. It may have a structure like this and so on. Now my intention will be always to convert all these kind of graphs which are not really symmetrical into a graph which looks like. I think we may have to close this call now. I see there are a lot of let's say disturbances in the internet. Maybe this is purely on my side, or there is some kind of a problem with Zoom today. I'm sure the entire session was already recorded, so I don't see any problem with the recording or with the video. But I do see a problem because if there are frequent disconnects like this, then we are also getting, let's say, disconnected from the subject itself, right? So let's try to continue tomorrow and let's see how it goes. I'm sure either my internet or Zoom has some kind of problem because of which this is happening. Okay, so let me share the notes. I'll also share a few more things which you can read, but I would like to request you not to overread. I'm simply going to share you a few pages from the internet, specifically a page which I like a lot. I'll share that page with you so that you can get some idea about what is a binomial distribution. Let's continue tomorrow so that we can look into how we can possibly do some kind of inferencing, or how we can mathematically define the binomial, let's say, distribution, which I wanted to avoid because the mathematics is really complicated. We really do not need to know, or we really do not need to memorize all the formulas. We just need to look at the formula and we need to understand what is going on over here. So that's we can do in the next class, and then we can also look into something known as MLE, which is known as maximum likelihood experimentation or estimator, okay, or method of moments, right? So this is something that we can look into in the next class. This is applicable onto binomial distribution only, and this MLE or method of moments helps us to do estimations or inferences. We have not looked into statistical inference yet, but it will be a good time to quickly introduce why these distributions are so important, because they actually help you do statistical inferences. Okay. Okay, I think we can make a close now. See you tomorrow. Thank you so much. Are you guys still there? Hello. Okay, I think I'll make an end. Thank you.